It's an honor to be here again. Spoke last year about CEAC, which is our research-grade engine educational interface to a habitat simulator. And now today I have the privilege of talking about SAM, which is an actual real habitat analog being constructed at the Biosphere 2. So again, my name is Kai Staats. I'm a researcher at the University of Arizona, which is the owner of the world-famous Biosphere 2. And I'm actually talking to you today from my apartment here on campus at Biosphere 2, which is a lot of fun. So I'm going to give you just a brief introduction to the Biosphere for those of you who may not be familiar with it. The Biosphere 2 remains today the largest and most audacious habitat, an off-world habitat analog. And it was a 3.2 acre facility with solid stainless steel floor, fully pressurized environment, dual lungs for the buffer capacity and automated fluctuation or adjustment to barometric pressure change. And of course, as a rainforest and an ocean and a garden and a desert, and just continues today as a leading indoor, but no longer sealed, research facility for climate change. So when this building, before the Biosphere 2 was built, there was the test module. The test module was constructed in 1987 by the Biospherians. And this was the first prototype, or actually the second prototype, and a fully functioning prototype, also with stainless steel floors, completely sealed glass windows, and a miniature lung that again automated the pressure, or conducted the automatic pressure regulation. I'll go into a little more detail on that later. So this is a photograph from 1987. I love this photo. This is the original Biospherians and their first time entering. The longest stay in here was 3 weeks by Linda Lay, and Linda is featured in the film Spaceship Earth. If you haven't seen it, it's a great documentary film from last year. She was inside for 3 weeks, completely hermetically sealed from the outside world. All of her air, all of her water, all of her food, and all of her human waste fully recycled internally within the structure. So after about 2 years of development and an effort and fundraising, we had our first fundraising round, and we had the ability to go in, we're given permission to go in and start refurbishing this system. This building had not been used for 30 years, had not been sealed. It had been used once as for a plant ecology experiment, but not in a sealed fashion. And so this is my associate Trent Tresh and myself on January 22nd of this year with our tools in front of us, and we were just overwhelmed. If you've ever lived in the desert, you know how much the desert can wreak havoc on things in just 6 months, let alone 30 years. And so we dove in, and we were grinding, and we were vacuuming and rewiring, and we were up in the rafters, cleaning. We had to spray everything down multiple times. We removed a 3,000-pound heat exchanger and replaced it with little mini splits that you can carry under your arms, reducing the power consumption by a factor of 10. We sanded and painted and primed and sealed. We even coated all of the upward-facing glass with 100% pure silicone as a means of reflecting almost 100% of the optical light transmission in order to simulate what would be more realistic for a greenhouse on Mars, meaning that it'd probably be underground or under regolith or in a cave like a lava tube. So because we can't bury the structure, we wanted to at least reduce the light internal to the structure to simulate that of being on Mars. And we also applied window tint, which gives a 50% optical transmission. So again, even the horizontal light is simulating what is on Mars. So we did our best to apply science endeavors at every step of the refurbishing construction phase. We're also working with Smith Aerospace Garments, which is the for-profit arm of Pacific Spaceflight. And this is Dr. Cameron Smith came out and brought a prototype spacesuit, a full pressure suit, and Deputy Director of Biosphere 2, John Adams, put the suit on, was inside for a full hour doing a series of tests in and around our analog. And that was a lot of fun. So we now have purchased and we will receive shipment this week of 2 brand new spacesuits. So all of the folks coming to our analog will be wearing spacesuits when they leave through the airlock. And here's a picture of John Adams up on top of the lung. This was a really fun day. I think he really enjoyed it. He said it gave him a completely different experience of what it means to be an astronaut in a pressurized suit. Even at 1 psi, mobility is quite challenging. 1 psi over ambient, that is. And continued efforts. We had to repatch the lung where the rats had chewed through it. We rebuilt the entire pressurization system with large caps and valves, installed new air conditioning. Our first crew quarters, which is in the form of a shipping container, arrived. We have another one arriving next week. And we resealed the entire lung, which again, I'll explain a little bit later. That was a major undertaking, but fortunately it worked perfectly. So this is a 3,500, 3,800 pound pan of steel that is floating on a cushion of air produced by a 1/2 horsepower motor. And this lung is what produces the positive internal air pressure for SAM, for the test module. And I'll again go into a little bit that later when I show you the data from the first sealed test. So we had a wonderful set of volunteers from all of the United States and from Peru and from the Navajo Nation. We had the wonderful, it was awesome. Shannon Rupert from Mars Desert Research Station sent her niece, Linnea, and also her associate director, Attila, to come down. They spent a week with us just working really hard. They were scrubbing and grinding and painting, not fun stuff, but they just dove in and didn't complain for a second. So thank you again, MDRS, for the assistance. And for helping us get this whole thing going. And this is how it looks today. It was 6 months of effort from January through June. And we're now, as I said, moving into building the crew quarters, which, as you can see, those 2 white horizontal panels on the right-hand side, those come out and are replaced with a doorway that will move into the crew quarters. So you can move from the greenhouse structure into the crew quarters and still maintain that hermetic seal. This is an artist rendering by Brian Vierstig. If you have a chance, go to spacehabs.com, just a brilliant artist. So this was his rendering. We've modified the design a little bit, but it gives you a sense of how this will look when we're done. And again, artist rendering of the interior of the rebuilt and refurbished test module, which will be our controlled environment of the greenhouse. And again, just our initial rendering of how we may build this out. We've changed the layout just a little bit. We're not going for a full 40-foot shipping containers. We're going to have one 40-foot and one 20-foot, and then hopefully next year add on an inflatable instead of doing all rigid structures. So we have a little more research capabilities to test different types of structures in different situations. And this is pretty close to what we're going to be doing. This is one of the existing greenhouses that we used in the 1980s and 90s, early 90s, to harbor the plants that the biospherians had collected when they sailed around the world before they moved them into the actual biosphere. So we've torn down 5 greenhouses and retained this greenhouse, which we're rebuilding the roof, and we're building a 6,400 square foot concrete crater inside that'll be painted and sculpted to look like a real Mars crater. So when you exit the habitat through the airlock, you will feel like you're in Mars. It's going to be fantastic. And then in addition to that, we have an exterior. This is our indoor Mars yard, and as you move through that, there'll be an exterior 1/3 acre Mars yard that we can sculpt to the needs of each team that comes through if they have the funding to make that possible. We're also working on a gravity offset rig. We're working with one of Hollywood's top stuntmen to design our gravity offset rig, and we're going to be building a very small neutral buoyancy tank using an old fish aquarium that we found on site. It's big enough for 3 people with scuba gear. So I laugh because it's going to be fun. And then if we get the funding, we'll move it to something larger, probably not as big as the one in Johnson Space Center, however. And also want to just briefly mention that CEAC was my principal presentation last year, so it's kind of been fun to switch this around because I closed out that presentation by mentioning SAM, and now we're talking about SAM, and I'm going to mention CEAC. This is the research-grade computer model and educational web interface hosted by National Geographic. It's up and running right now. It's free to anybody in the world, and I currently have an Arizona State University capstone team, engineering capstone team that is building a new back end so that we can receive live data from SAM, and anybody in the world can log in and watch that data in real time on this interface. We'll be developing some new panels and ultimately capturing that data and using a reinforcement artificial intelligence algorithm, training CEAC to be the manager of the plant growth and life support systems within SAM. That's a couple years down the line, but we have all the foundation for that. So just a brief summary. I won't read these to you. You can see it. You can always look at the slides later. This is our schedule. We're currently in stage 2, working on the crew quarters, the initial Mars yard, rudimentary, and depends upon how much additional funding we get this year. And we are expecting to have our first research teams arrive in May, and we're open to registration now on the website. So this is what you came to hear about. Thank you for letting me give the brief history. We conducted our first hermetic seal of SAM on Tuesday, June 29th, 2021, just this year. We had 5 people, including a reporter from Harper's Magazine, embedded in our team for 4 hours. And we had 3 sensor arrays, 1 external, 2 internal. 1 was internal in the open room, 1 was internal sitting inside of the CO2 scrubber itself. The CO2 scrubber was designed and built by Paragon Space Development Corporation for NASA, and that's been donated to us, and we've remodified that from soda lime into zeolites, and I'm now working on a swing bed system so we can adsorb and desorb and release the CO2 into the test module, the greenhouse. So this was the basic timeline. It was a 4-hour test from 4:02 to 8:02 p.m. And again, don't need to read the slides to you. You can see approximately what happened at each one of those stages. And we had some plants inside some of the students from University of Arizona CEAC, which is an advanced agricultural research center. They brought up some hydroponic system installed the day before. Honestly, this was for the photo shoot and just to have something living inside. They're not mature enough to conduct any significant CO2 sequestration, but we did end up eating them later as they were all edible. We also were playing a board game called Extranaut, which was developed by the PI of OSIRIS-REx, which is pretty cool. It's a fun game. We ate NASA-approved Doritos, and we put together a farm bot. So we had a lot of fun in those 4 hours. We got a lot done. This is a bird's eye view. I climbed up in the rafters and took a shot of our team, and that's Trent and Katie and John. John Adams, again, the Deputy Director of Biosphere 2 in our test module during the sealed experiment. And what was really cool is all the family and friends came from around the neighboring towns and such, and were just outside kind of cheering us on. We had a film crew and somebody running, just monitoring everything from the outside as well. So it was a lot of fun for our first test. So now I'm going to run through the data and hopefully have plenty of time for questions and answers. I don't want to consume too much more time. So we were using Veneer brand sensors, and we recognize that those are typically they're higher quality than what you might get for a Raspberry Pi, but they're also not your highest quality sensors. But we feel that for what we conducted in this experiment, they were more than adequate, and we have the full support of the Veneer company, which was outstanding. So we monitored pressure, oxygen, temperature, CO2, and relative humidity. And I just want to quickly go through and demonstrate that we conducted our science correctly. We established baselines first, just short 6-minute baselines to demonstrate that all the sensors were functioning as expected. And again, these deviations, you have to remember what these deviations represent. These are just a few parts per million. And it's also typical as a sensor adjusts to its ambient temperature, there'll be minor fluctuations at the start. And for oxygen, and for temperature, relative humidity. Temperature and relative humidity are built into the CO2 sensor because it's a self-calibrating sensor in the sense that you have to take into account temperature and relative humidity when using a CO2 sensor. Otherwise, you have to have external sensors to do the same thing for that calibration or for that cross-reference, because the CO2 will appear to increase and decrease based on those two functions. So I'm going to walk through just 4 slides of data and kind of describe in some respect what we saw. Some of these things were as expected. Some of them caught us off guard. It's our first time doing this, and we had to scratch our heads and do a little research to figure out what exactly we saw. This one makes sense. This is the pressure. So you can see the internal pressure is the green, the external pressure is the red, and so the red stays relatively consistent, and the internal pressure rose as expected when we turned on the blower, when we sealed the door and turned on the blower about 20 minutes after we were inside, and the pressure rose very quickly, about 1/2 of 1 psi. And the CO2 readings, now this is one that threw us for a loop. We expected the CO2 to rise, and it did. You can see the red and the yellow. Now the red is the general CO2 in the room. The yellow is also the CO2 in the room, but sitting right in front of the intake of the CO2 scrubber. So they're relatively similar, or should be relatively similar, aside from small pockets of CO2 which exist. But the green one, you might think, what in the world happened? That's inside the scrubber. Well, it caught us off guard as well. Why would it go from so low to so high? Turns out that it makes sense that the CO2 scrubber has a sealed chamber. We had placed that CO2 sensor inside that chamber. So it didn't see the increase in CO2 until we activated the scrubber towards the end of the experiment, at which case it got its first breath of the ambient and quickly rose to match the CO2 in the rest of the room. So at first we thought something went seriously wrong, and then like, wait a minute, this makes sense, which is just good adventure in data. I love it. It's fun to try to figure things out. And the oxygen, again, this caught me off guard, but if I had really thought about it, it shouldn't have. There's so much oxygen in an 11,000 cubic foot space with 5 people. You're going to have to run the sensors for a long time and run the experiment for a long time before you really see an oxygen deprivation. Remember that as we take oxygen in, we're also breathing oxygen out. We're not consuming every molecule of oxygen that enters our lungs. So this really does make sense. And those minor fluctuations are probably temperature derivatives or temperature associations, if I remember correctly. So again, performed as expected. I just had to think about it a little bit. And finally, everything else, temperature, relative humidity, acted exactly as we expected. A small deviation because it was actually cooler inside the test module because of our mini split cooling, because of the heat pump, than it was outside. Therefore, if you remember, relative humidity goes up as temperature goes down. So we saw slightly higher relative humidity inside, partially because we were breathing, partially because it was a lower temperature. Now, this is the fun part. This is our last section here, and then we'll go to Q&A. This is the lung, one of 2 lungs that maintain the positive internal pressure at the Biosphere 2 when it was in operation. Now, this lung is artificially elevated using a 5 horsepower motor. It really is as big as it looks. This is enormous. It's a 40,000 pound plate, 40,000 pounds of steel and concrete floating on a cushion of air. This is not an optical illusion. It really is floating. That cushion of air is created by a vacuum or a partial pressure differential above the membrane, the rubber membrane, by a 5 horsepower motor. It's awesome. So they inflated both of the south and the west lung when before the Biosphere was started. And this is the buffer of air and the automatic compensation system for temperature and barometric pressure differentials between inside and outside. So they didn't blow the windows out. If you didn't have this, your windows would blow out before your first 24 hours was up. So we have the same thing, much smaller. Ours is a 3,000 pound. We also inflated basically the lung with a blower, a 1/2 horsepower motor. And that's what maintains our internal positive air temp pressure. Now, we wanted to figure out how much our lung weighs. Remember that our test module had not been used for 30 years. And although we're in contact with all of the biospherians, Tabor and Jane and Abigail and Laser and Mark, they don't have necessarily the documentation anymore either. Nobody knows how much this thing weighed originally, or at least we couldn't find it. And so we did a little math. We used the square foot basically of the pan, what we call the pan, which is the steel plate, and we figured out what the total surface area is. And then we knew that we had a 0.05 psi differential in the elevated when we pressurized the room. And so we were able to do the math, and we came out to about 3,800 pounds or 1,700 kilograms. And we did it both by pounds per square inch and kilopascals and kilograms per square meter. And then we went back to the biospherians and said, does it sound right? Does it sound about right? And they said, yeah, that sounds right now that they heard the numbers. So, and it looks about right too, when you look at the size of the metal, you do some other estimations. So that was fun, just to use some basic arithmetic, a little bit of head scratching, and be able to use the data we collected as a means of reverse engineering and calculating the mass of that lung as it exerts a positive pressure on the column of air beneath and therefore inside of the test module. So that's the end of my slides. As I said, I wanted to keep it short and sweet so we have a chance to talk. But I also want to remind everyone that while we are working on a Mars habitat, and it's terribly exciting for our species to become interplanetary, at SAM we have a very important mission objective, which is to engage research teams from around the world in hands-on scientific discovery and to inspire the next generation to be engaged custodians of this planet while we're exploring new worlds. So much of what all of us in this conference are learning can be applied right here, right now, whether it's improved agricultural systems or CO2 sequestration systems or water recycling systems. Everything we're doing is beneficial for both worlds. And that's something that's really important to us, especially under the flag and the banner of the Biosphere 2. That was the mission of the first Biospherians as well. So again, team registration is open. I have to put on my sales hat for just a moment. Team registration is open for 2022, and we already have 3 teams signed up. We're probably not going to be taking teams into June. It gets pretty hot here. And even if you're inside air conditioning, it's miserable when you go out in the Mars yard. So we'll probably be closing down team stays in May and then opening up again in September, October of 2022. So we look forward to those of you who are ready to come into a hermetically sealed habitat. Thank you.
Thank you so much, Kai. That was a wonderful presentation. So we're now going to open up for Q&A, and there are a couple of questions in the chat. So please type your questions in the chat, and we'll get to them. So there's a question that's asking from Dusty, and asking, would any sealed habitat need some sort of lung like this on Mars or Moon?
Really good question. Thank you. No, this is one means by which you could contain your air. It's rather elaborate. What I like about it is that the lung is completely, once it's inflated, it requires no motors, no electricity, it just works. And knowing that all systems have leaks, everything has a leak at some level, the lung will not stay inflated forever. But what I like about it is if you had, let's say you had a pressure break somewhere, you had a small crack in a window or an air seal broke, the lung automatically, it's already pressurizing that vessel. So yes, the lung would come down, but it would give you that buffer of air. And so even the Biosphereans, in the original Biosphere 2, it lost about 10% of its volume per year. But so after 2 years, it was only 20% lower than it was when it started. So in theory, you could go for several years. The other means of doing this is, of course, compressed air. You can compress air into 2,000 or 3,000 PSI canisters, and you can have automated release functions. In fact, to finish up this question, earlier this year, we just finished work with a University of Arizona engineering capstone team, and they built I should have shown it, they built a fully functional prototype of a completely automated, driven by a Raspberry Pi and Arduinos, automated pressure, basically a pressurized atmospheric compensation system. So it both drew air in from the habitat, compressed it if we were overinflated, and then spit the air back out again if we had a leak. And they were able to simulate that in the Raspberry Pi. It was a 10th scale model, but we're actually taking the exact Raspberry Pi, the same software, the same pump, and just hooking it up to a bigger tank. So those are two immediate ways that I can think of. A lung would work on Mars. It's just not required because your atmospheric barometric pressure changes will be nominal, very, very small on Mars, and non-existent on the Moon.
Right. So there was a second part to the question. So that Dusty asked, what about other sealed vessels, for example, like rovers, etc.?
Yeah. So again, if you're on Mars, well, if you're on the Moon, there's no atmospheric pressure differentials to be worried about at all. So you only have to worry about heat differentials. So if you are in open sunlight, if you move from the shaded side, from shade to sun on the Moon, or as its 2 week long night passes into day, if you are heating the air inside of your vessel, if you don't have some way of blocking that infrared, if you're heating the air, you will have a much greater positive interior pressure that you have to contend with. So if you're maintaining your vessel at 14.7 or even 12 or 9 PSI, but it doubles because of the heat, you have to be ready for that. And you probably don't want to blow it off because then you're losing breathable air. You might want to draw it in and pressurize it in a smaller tank and then release it again when it cools down later. And again, I'm not an expert in what you would actually do on the Moon, but that's my immediate intuitive response. On Mars, the atmosphere is so thin, I'm imagining that the pressure differentials with different night and day and such would be noticeable, but probably not enough to cause windows to blow out. Your windows are already going to be secured just because of the massive pressure differential between your inside pressure and your outside pressure being essentially zero.
Wonderful. Now, Adil asked, what is SAM-B2 and what does the lung do again? Maybe give a 6th grader version, simplified definition of the lung.
Sure. So SAM is a space analog for the Moon and Mars. So it's an analog as so many of the other incredible analogs in the world. The difference is that ours is sealed. It's hermetically sealed. So once you lock yourself inside in SAM, you're breathing air and you're drinking water that's been recycled over and over and over again using mechanical and eventually plant-based systems for those recycling. And the lung is just like it sounds like. It's this inflatable cavity that can expand and contract, but to maintain a positive internal pressure. So the lung is always kind of pushing down because of the weight. I'm trying to think of a good analogy. Maybe like a bicycle pump. You know, when you push on a bicycle pump, it's forcing higher pressure air out the nozzle at the end. This is essentially a big fat pump that you push only once.
Thanks.
How's that?
Yes, that was a great definition. Now, Dusty asked, have you heard of what was to be the largest dome in the world called the Minnesota Experimental City, and designed by Buckminster Fuller, father of the geodesic dome, and I cannot say this name, Atheslan Spillhouse, a visionary.
I have heard of it. I haven't read much about it. I do know that Buckminster Fuller met with the Biospherians early on, and he encouraged them to build this. He was very motivational and said, you have to do this. I think he met with Ed Bass, if I remember correctly. I'll have to go back and watch the Spaceship Earth again because they mentioned that. So I know that Buckminster Fuller was directly involved in at least initiating the concept. And of course, the space frame is entirely from his design of those geodesic domes. But no, I'm not very familiar with that particular concept or that particular design.
So maybe I can ask you a question, and please, yes, if you want to ask, we've got a couple more minutes. So yes, please do ask Kai more questions. But let me ask you this question, Kai. How do you qualify as a team or as an individual to come into the Biosphere, to the SAM-B2?
Yeah, it's a good question. Thank you. So the qualifications are, you don't have to be a scientist. We do accept artists. We can accept artists as embedded in a science team, or we can even accept an entirely art, film, writers, sculptors, painters team. We have one of the teams that's lined up and wanting to come in is entirely art driven. So, but as a researcher, for the research teams, you do need to submit your concept for either one total project that everyone's going to be involved in, or each one of the science objectives of each one of the team members. You need to explain what you need, how much power, how much water, are you going to manipulate the air, are you going to manipulate the plants, are you bringing plants with you? We need you to define your science experiment, what your objectives are, what your hypothesis is in broad terms, and what you hope to achieve. We need to make certain that you're going to be safe. So we need to make certain that what you're bringing in is first and foremost safe for you and the crew, because it's sealed. You can always leave if there's an emergency, but we don't want to disrupt the other experiments that might be running, nor in any way endanger your health. Number two is we want to make certain that you have a good experience out of this. We want you to come away with something that's publishable. It's not guaranteed, it's not mandatory, but we'd love to see you publish what you learn from this experience in peer-reviewed journals. So we're going to help guide you through the preparation of your science objectives and maybe help move things a little bit if we think you can do better by this or better by this. Yeah, so it's really a conversation. We have a team at the University of Arizona that we're reviewing those proposals, and again, clarifying and filtering and making certain that you meet the basic objectives that are required to be in SAM.
Great, and so there's another question. Well, I'm going to ask the question because nobody's posing a question, but I think my question is like, if you are going to bring in a scientific study project, do you need to get IRB? And secondly, are there any financial support for anybody or teams from your end?
Really good questions. So the IRB is required anytime you monitor and capture or record for publication human-related data. If you're capturing data about even somebody's body temperature or skin cells, anytime it's related to an individual person, a human being, you have to have an internal review board. You have to have an IRB approval to make sure that you're doing that in such a way that their data remains anonymous or is published correctly. And that's been true for a number of years now. So it's a known process. It's a little bit arduous, but it can be done. And sorry, the second part again?
Oh, the second part of the question is, do you provide, or is there any kind of financial support for the individual or the teams that submit from your side?
So we do have our first sponsor, which is kind of exciting. There's a company, I'm not prepared to name the company yet, but we've had a company step up and they have decided they want to sponsor 3 teams. They will be sponsoring the stay in SAM, which means the teams will only be responsible for getting to SAM, essentially. We're working out the details and the exact finances. So I believe that along the way, we're really hoping to bring in as many sponsors as possible. And these folks were just so proud. They stepped up and they said, yes, we want to commit to this. this, and they want to see 3 very different kinds of teams that represent maybe different ages, different backgrounds, and maybe even different financial capabilities. So I believe that as we continue, as with MDRS, as with other analogs, there have been and will be sponsors who make this possible for teams that might not otherwise be able to come here.
Well, on that note, thank you so much, Kai. This is an amazing presentation, and we will need to now move on to the next session. We'll close this as a Zoom room, and see you on the next session, everyone. Thanks, Kai.
Thank you, everyone. See you at SAM. Bye.
Take care. Bye-bye.